TedSpeers is a technical fellow at Microchip's FPGA business unit, where he is responsible for defining its roadmap for low power, secure, and reliable FPGAs, as well as SoC FPGAs. Ted is a RiskFive leader and evangelist, and has served on the board of directors of RiskFive International since its inception in 2016. He joined Actel, which is now part of Microchip, in 1987 and held roles in process engineering and product engineering before assuming his current role in 2003. He is a co-inventor on 35 US patents. Prior to joining Actel, he worked at LSI Logic. Ted has a Bachelor of Science in Chemical Engineering from Cornell University. The title of his presentation today is RiskFive and the Future of Computing. So, ladies and gentlemen, please help me to welcome TedSpeers.
Thank you for that introduction. Let me see. So I'm going to start sharing. I think that's how it's supposed to work. Share screen. Share that screen. And start from the beginning. People see that?
Not yet.
Not yet.
Oh, great. Got the latency here. So that wasn't showing. Let's see here again. Share screen, screen one. Okay, maybe that's my problem there.
Okay, we saw it.
We can see something.
Yeah, so how about that?
We see your email, not the slide. So the slide in the front. It seems the email is in front.
So why is it sharing that screen? So we should have, sorry about this. Share screen. Okay, one more time. I can do this. Okay, that screen to, sorry about that.
Yes.
Is that better? All right, sorry about that. You know, I don't know how many times I've tried that. All right. Okay. Yeah. Thank you very much for the introduction. Yeah, my name is TedSpeers, and my talk is RiskFive, the future of computing. I definitely appreciate the opportunity today that CASPA is giving me to speak, and hopefully after today you'll want to have me back. All right, so about me, I think that's all you need to know. I got my WeChat QR code, social media, I'm at TedSpeers. And I think we've gone over this. I did graduate from Cornell University. What's a little bit unique about me probably in this audience is my bachelor's degree is actually in chemical engineering. Technical fellow at Microchip FPGA business unit, and the member of the RiskFive International's board of directors since its inception. So definitely proud of my role there. I've been an active promoter of RiskFive, spoken at 16 events. This is, I guess, number 17. And, hundreds of people around the world heard of RiskFive for the first time from me, I'm pretty sure. I also drove the creation of the Security Standing Committee. One of the attractions to RiskFive and our organization initially was the opportunity to kind of get security right with RiskFive. And so security is a first-class citizen in RiskFive International. And, most recently I recruited our CTO, Mark Himmelstein, who I'd recommend you guys invite, but the organization has made huge progress as far as its productivity, thanks to Mark's leadership, and you'll see some of that today. So the content today, I will indulge myself and talk a little bit about the Microchip FPGA business unit. I'm actually representing myself today, but Microchip FPGA business unit is a big part of myself. share some RiskFive International news, and then talk about the RiskFive Vector ISA, give you a brief introduction into that, and some examples, and then start talking about an emerging pattern in compute, give you some examples there, and then pull it all together, which I'm going to call a framework for the golden age of computing, and then finally some calls to action. So our FPGAs, we have a flagship family is called PolarFire, and it comes in two varieties, an FPGA and then also an SoC FPGA. So that means a microprocessor is embedded with the FPGA. And we're distinct because it's a RiskFive microprocessor, quad-core application processor based on the Cie5 chip. So we're one of the first RiskFive chips out there that you can actually program with. There's 2 billion RiskFive devices have shipped, but most of them are deeply embedded, so the user is not programming them. So to support PolarFire SoC, we've built an ecosystem to a RiskFive based ecosystem to support PolarFire SoC. So that's all the ecosystem type stuff, tools, boards, OSs. It's all part of the ecosystem, and it's pretty sizable at this point with some pretty famous companies involved, including example Green Hills Software, mission critical for a lot of industries. So we have a board, the first board out, it's called the Icicle Kit. So you see there in the middle, the Microchip RiskFive shiny PolarFire SoC device. So this is a basic development board. But our partners make boards as well. So you can get boards from these six companies shown here for different form factors and domains. And then we also introduced what we call the Smart Embedded Vision Kit. So this PolarFire SoC, you can hook it up to cameras and displays, run your vision stack on the RiskFive, and then do any kind of vision acceleration using the FPGA fabric. So I've been sharing this. This is how we view the compute, and been sharing this for a while. It's not that unique at this point, but on the left there, you see devices and sensors, and actuators. I kind of view those as the nerve endings of a being of some kind. The cloud represents the brain, and in between, you've got kind of the nerve centers or the nerves transporting the sensors all the way up to the cloud. So megatrends here, we've of course you got exponential growth in IoT of the sensors, and there's increasing human-machine interaction there. In the brain, cloud, massive data is being processed increasingly, but there's a problem where there's a latency between the sensor and the cloud. So more and more compute is being moved into the edge, so-called edge, so you can handle all these sensors more locally. So power used to be, not customer would say they were interested in power, but they wouldn't really make buying decisions. But now power is almost the primary factor. Whether if you're at the edge or the sensors, you care about supply or battery life. If you're in the cloud, you basically care about your electricity bill. You're paying $6 per watt per year in this massive facility. It's best to last 20 years, and you want to improve its productivity all the time. And then in the edge, it's almost about moving heat. This is where you see fanless, on-premise or outdoor enclosures. So it's heat removal. It's the power problem in the middle. Solution trends. We already talked about pushing compute loads from the cloud, from to the edge and to the devices. Heterogeneous compute paradigms and accelerators solve some of the power problems today. Hardware and security solutions for the device. So it used to be if all the compute's done in the data center, it's behind guards and gates and guns. But now your compute is being deployed out physically where it's reachable. So you have to have hardware security. And then safety and reliability is increasing because of the human-machine interactions. So where our FPGAs fit in is kind of in here, really at the edge. We're not the microwatt FPGA, and we're not the data center FPGA, but we really fit in here where you want to accelerate without heat problems, securely and reliably. So we are very differentiated in these areas. So we operate in the harshest environments. And if you want to talk harsh, and we're talking Pluto, Jupiter, Saturn, Mars, those are pretty harsh. And also any airplane you fly today has hundreds, if not thousands of our FPGAs on that. We have unique features that make us reliable. Womb to tomb security, and basically when our chip comes out of the fab, first thing it sees in life is an HSM, and we're injecting keys into our devices through the whole manufacturing process, and then we can carry it on so the customer can then layer his security on top of the secure HSM secure base that we've already established. So with this, you can secure your supply chain, and then you can also secure your data in your application. Then finally, low power. This is a competitor FPGA. This is in the lab running an application with an infrared camera, and you see that max is about 75 degrees centigrade with the competitor FPGA. So same environment, but polar fire FPGA, basically full 20 degrees lower. So you imagine what that has to do in a real environment where the ambient is not 25 degrees. Our low power, we like to joke, our goal is to put fan companies out of business. So hopefully not putting any of you, our listeners, out of business here. But also we make the impossible possible. We can make people build equipment and form factors they couldn't do without our FPGA. So they're not lining up to give testimonials because in many ways, polar fire is the secret sauce in their equipment. So moving on to RiskFive, big year last year, like I mentioned, over 2 million devices, but this was recent news. Intel joins RiskFive International. The headline is a little bit fake news. They definitely created a $1 billion innovation fund. RiskFive is a key part of their innovation fund. So if you have a RiskFive solution, RiskFive IP, they're willing to invest in you. I do want to mention that Intel is also proud of the fact you can get, they actually support ARM as well. But I showed their innovation partners that are all part of the RiskFive International there on the right. So then, speaking to our CTO's ability, we ratified 15 new specifications at the last summit. So that was great progress. Excuse me. Click 1, 2 quickly. All right, so the vectors is what I'm going to talk about, and then illustrate some examples with Andy's in Sci5 in the talk here. So let's look at the vector ISA. So RiskFive is an open standard, so everything, all the specs are available on GitHub. But the core of the vector ISA is the 32 vector registers of a certain length. It's a variable length. It's up to the implementer, but the maximum they could choose is 2 to the 16 or 64K bits. So you got these 32 vector registers on your chip, and then we have what's called the state registers, configuration state registers, and one of them is read-only. It's VLEN-B. So when you have to decide how big your vector engine is going to be, or how big, and that's basically the length of that vector. So that's encoded in hard, and so the software needs to read that to actually figure out how to run. But we'll use this example of VLEN-B at 32 bytes or 256 bits. So another vector is, or register is V-type. So this one is writable. So your code is actually while it's executing, you can actually change the V-type, and this actually configures what really is a very flexible register file. So some of those things is the element width. So we can set the element width from 8 to 16 to 32 or 64, and plans to go even bigger. So the element is basically how much data do you want to operate on each vector element. So we'll take an example here of element width of 64. So basically we can put 4 vector elements in one of these 256-bit registers. Then there's VLMUL. So this is actually the register grouping. You can group registers together. So you can, at the bottom there, 8. You can take 8 of those registers and make them 1, or you can actually, so that the 32 become 4, or you can actually go to partial. So if you use 1/8 mode, you could get 8 times 32 is 256 registers. So in this example, we'll set this to 2. So now grouping two registers together, we basically can have 8 elements in each register. So once this is set, every vector instruction is going to be working on 8 elements because you've set this. But you can change this as you run through the code. You can reset this type vector. If the nature of the vectors you want to operate on change, you basically reconfigure the vector file. So we'll run an example here on the bottom left. I got vector instruction vadd.vv. So VV means vector vector. So we're going to add 2 vectors together. I could do VS, add a vector to a scalar, or SS, add 2 scalars together. We're adding 2 vectors, and I've, before this meeting, I preloaded these V0 with 4 integer 1s and V2 with 4 integer 2s. And what we're going to do, V0 and V2 are the source registers, and V4 is the destination register. We're going to add all of these using that ALU at the bottom. But there's only one ALU, but one instruction is going to automatically add each element together in serial to become 3. Uh-oh. That's not right. Someone screwed the ALU up. That's not a feature of the ISA. That's an implementation error, I swear. But actually, it's a joke. What we really want to do is take advantage of some of the parallelism here. So now I'm actually showing an example of you can implement the ISA many ways. So here I want to do 4 additions in parallel. So now I'm going to add these 2 integers together, and in 2 clock cycles, I'll get get the basically compute some 4 vectors together, or some two vectors of length 8 together in 2 clock cycles. So it kind of illustrated the power here of the configuration, dynamic configuration of the register file, but also, and this basically means one instruction set can operate with many different ways of, many different hardware implementations. So we'll kind of take these to examples. So this is a slide from Sci5. So Sci5, Krista Asanovich basically created RiskFive and led the development of the RiskFive vector ISA. But you see there, kind of, what does RiskFive offers? It greatly simplifies software development across a range of vector processors. I think that was illustrated. Change of vector length, and we have a vector length agnostic architecture. So the same instruction set works on any length of vectors, and then you could dynamically modify that register behavior, and that actually creates most efficient computations. So you can change how those registers behave to match your application, and therefore handle a broad range of applications. So to illustrate some of the flexibility, Sci5 offers 2 classes of processors with vector processors, their performance series and their intelligence series. And so you see here, the performance series got a 256-bit register vector unit, and then the intelligence series has 512-bit vector units. So this shows an example of one ISA, one set of programs, different configurations. Then a key thing here about RiskFive is they've added extensions to these. They have 5 Sci5 intelligent extensions. That's one of the beauties of RiskFive, that you can extend it. But the base ISA is there, and it's going to be constant, but you can actually differentiate yourself as a company by building on that with your own extensions. So another company, Andes, they were important to the RiskFive ecosystem. They're based in Taiwan. They had their own ISA, and when it was decided to come up to the new 64-bit architecture, they said, well, let's choose RiskFive. So Andes has actually gone from their own proprietary ISA to RiskFive, and they have a vector processor called the NX27. So kind of make the same points here. You can extend it. So you can, with the ACE extensions, a standard interface cache coherent interface. They can extend their vector processors, and then just like SiFive, comes in many different flavors. You can tune the vector length, and you can tune the power of your processing unit. So, many applications vector processing applies to, so matrix multiply, FFT. So cryptography is an interesting one. So in fact, RiskFive has a crypto spec for scalars, but they're working on a vector crypto spec, which is going to take the RiskFive vector ISA and add some crypto extensions to massively accelerate crypto using the vector extensions. So it's kind of putting into practice what I already talked about. So I like this slide a lot. It's basically my slide. On the top is the cloud computing, and the bottom is the endpoint. The middle is the edge. One ISA, one processor architecture can be tuned for each of these domains. So here they're using 128-bit data path for the endpoint, all the way up to 512 in the data center. So kind of just illustrating both my initial point and the beauty of the RiskFive vector ISA. All right, so switching to emerging patterns, I'm going to take you through a couple examples. This is a product from Xilinx. It's called their Versal AI chip. It's their flagship. And kind of up there, you see with their AI engine array. And so if you look at that, that's basically a 2x2 matrix of what they call AI engines. And then if you drill in a little closer to the AI engine, you'll see that it includes a 32-bit scalar processor and a 512-bit fixed point and floating point vector processor. So a 2x2 array of vector processors. Well, are they the only ones doing that? This is a pretty fascinating company here called Graphcore. They have something called the IPU, the Intelligence Processing Unit. This is 1,216 elements, and this, again, a 2x2 array. Drilling in closer, what is that? Well, it's a local memory and a core, which is a 512-bit data path, 16 single bit per floating point ops per cycle, 100 to 1.6 gigahertz. So that's 25.6 gigaflops per core, or 31 teraflops per IPU. And you could take this to extremes. If anyone's heard about Cerebras, a startup that but their chip size is the wafer size. So they have 850,000 cores in a 2x2 array. If you drill down there, I don't know the data width of their processor. I know it's optimized for sparse matrix processing, but a fascinating technology from Cerebras, but I think illustrates the pattern that I've been talking about. So looking at a company called Esperanto. So they're a part of RiskFive International. And if you look at upper right there, that looks familiar. It looks like a 2x2 array of something. Before I get into that, just a little bit about Esperanto. So the reason I'm here today is I forget the year, it may have been 85. The paper came out, the case for reduced instruction set computing, started a whole revolution, which industries are built on. And Dave Ditzel was one of the authors of that paper, along with Dave Patterson. Dave founded Esperanto. So looking at that, inspecting that 2x2 array, what is that 2x2 array? Well, there's 1,088 RiskFive, 64-bit RiskFive processors. Then each is attached to a vector tensor unit, illustrating the point again. In addition, on this chip, they also power it with 4 high-performance 64-bit out-of-order RiskFives on this chip. So this kind of illustrates, RiskFive lets you innovate. Where Esperanto is really innovating, actually, is in the power. Their chip runs on the x-axis you see there. You can run it down to, almost 0.2 volts. So you can run. If you want maximum performance, you can operate your chip at 0.9 volt at 275 watts, lower voltage at 0.6, but it actually runs down to 0.3 here. And you got 8.5 watts and 6 chips gives you 45,000 inferences per second. And kind of the optimum, throughput and power here's 6 chips, 20 watts total at less than 0.3. So a lot of capability, but they innovated where they mattered. The real innovation here is actually in their energy efficiency. So, look at again to kind of make that point again, all their instruction encodings follow RiskFive vector conventions. So that they produced this chip before the vector spec was out there, but you see there, it's got the vector operations that are actually part of the RiskFive vector ISA, but then they build their own extensions on their tensor operations and cache control operations. All right, kind of tying it all together. So in 2017, proud to say a colleague of mine on the board, Dave Patterson, won the Turing Award, along with his lifetime collaborator, John Hennessy. And their paper lecture was called A New Golden Age for Computer Architecture. And notice security is on there, but we focus here as domain-specific hardware and software co-design. They kind of illustrated the point here where you show Python on the top going down to Intel AVX, which is Intel's vector instructions. But as you move from the bottom to the top here, what you're doing is making the software developer more productive. But the software is actually accessing more hardware. So, as you move down further down the stack, the hardware is getting more and more productive. And so they introduced, there's a layer now on top of these languages that came out like Python. They now have what are called domain-specific languages, such as TensorFlow, that are built on other languages to add another layer of productivity that's available to everyone. So to me, kind of ushering in the future and the framework that we're talking about, it's really about bridging between these domain-specific languages and domain-specific hardware, and how that's going to be achieved. So, I think there's two things. You want to enable the flexible and fast creation of the DSAs, make this hardware quickly, this new hardware quickly, and then you ought to easily be able to target the DSL or a new DSL to the new DSA. We want a kind of a virtuous cycle where both of these ends of the stack are improving. So you take those requirements there. How are we going to do this? One is leverage open standards to enable sharing between developers and domains. Then we want to actually create DSAs by connecting and configuring well understood kernels of productive hardware. So we don't want to rebuild these DSAs from scratch. We want to create kernels that are kind of elevated to building blocks for these DSAs in a manner that both the hardware and domain architects could understand. So here I've kind of hooked them up as a graph, but 2x2 arrays work nicely as well. And then modify or create new DSLs to target this new DSA hardware. So this framework for the golden age of computing, first, I think there is not a productivity problem. There's lots of languages coming out that are helping people in all kinds of domain. I don't think this is the problem of getting new domains specific languages. But down here in the hardware, first of all, back here, I notice I fixed Dave's slide, replaced the AVX with the RiskFive instructions. But we do need help here. So we need more investment in hardware. I mean, to me, that means hardware startups. We need open hardware standards. RiskFive is definitely part of that. And then we need, ways to, major reduction in the time and cost to develop this new hardware. And we need more hardware engineers. We need to make hardware cool again. Everyone likes doing software. We want people to be doing hardware. Interestingly, in Taiwan, think it was 2019, I was on a panel and it was tweeted out during the panel, make hardware cool again. That's what RiskFive is all about. And the magic of the internet's, 5 minutes later on WeChat, I was quoted, and Rocky came through with me, and we've got hats for making hardware cool again. So that's the hardware, but then in the middle, we do need more focus on compiler technology. So actually, these slides I drew from the presentation I gave in 2019, but it's still relevant today. It's aged well. In fact, on February 22, Elon Musk tweeted out in response, compilers can be way better too. Not enough effort spent there. So when smart people agree with me, I'm not too proud to point that out. Speaking of smart people agreeing with me, Chris Lattner, who created LLVM, which revolutionized compilers, actually gave a talk when he was at Sci-Fi called RiskFive and the Golden Age of Compilers. He's delivered this talk in version of this talk many places, but I was honored to have him at our Mi-5 virtual summit last year in 2021, and he gave this talk. And it's not a 2x2 array of a parallel compute. He actually has a tensor of parallel compute. But how are we going to target or make this hardware actually productive? And so DSA compilers to the rescue was his point. And so he mentioned founded LLVM, but LLVM Foundation has a effort now going on called MLIR, which is basically multi-level intermediate representation. So this is now, instead of just compilers targeting scalar computers, they want these compilers to target this new generation of DSAs and actually help create those DSAs. So his concluding slide, I think makes all the points I'm making today. The pervasive RiskFive CPU ecosystem drives fundamental software. So, use the RiskFive like you saw Esperanto doing, the 4 controllers to control the chip. And then the RiskFive vector as perfect platform for the parallel compute. So you use those RiskFive vectors everywhere and then extend them further with additional capability as needed. And then, the MLIR compiler system will tie it all together. So you can innovate where it matters. All right, so getting to the call to action portion here. RiskFive, this is a slide from Mark Himmelstein, basically asking people to help contribute to RiskFive. And you have something called development partners. So you see the Chinese Academy of Science, Rios Labs, and IIT Madras all have these partnerships between professionals and universities, helping lift the RiskFive ecosystem. So we have opportunities. If you're a professor out there who wants to partner with industry, we are trying to recruit you to help us with compilers, hypervisors, application libraries. So finally, Microchip has 1,517 openings, not including the ALU verification. Please attend the Mi-5 virtual summit. Promise interesting keynotes such as Chris Lattner. And if you don't like fans, check out PolarFire, FPGA, and SoC. All right, I think that's it. I hope I'm on time. But if there's time for questions, let me know.
Wow, Ted, that was both extremely informational and I find it very entertaining. I love when you make hardware cool again. Like cool is double meaning, right?
Yeah.
I mean, because you talk about putting fan suppliers out of business.
I haven't even noticed that. You're right.
Here we go. Here we go.
Maybe turn into blue hats. Make them blue hats. People.
Yeah. So first of all, it's we mentioned in the intro, you have 35 patents. That's 35 more than I have. It's just very impressive. In the recent past, CASPA had a honor to invite the CEO of Xilinx, the CEO of companies like Acronix, to be our speakers, and it's very fitting to have you from Microchip to talk about FPGA and RiskFive related topics. So thank you for coming and sharing with us. So for our audience, if you have any questions for Ted, first of all, the second half of this today's event is a panel discussion. So there will be a more lively exchange, Q's and A's. And also feel free along the way, post your questions in our chat, right? So, that maybe we can respond to your questions during the panel discussion as well. So at this point, because of time, Ted, just very quickly, especially you have a very impressive academic background, and you're talking about making hardware cool again, and encourage young people to go into hardware, not just software. For the younger people among our audience, what advice do you have for them if they want to pursue the career that you were talking about, whether it's in Microchip or just hardware RiskFive related careers?
Yeah, so RiskFive definitely is a big part of it is the academic thrust. I mean, it's founded by preeminent hardware architects, but it's global, and whatever country you're in, I definitely should take one computer architecture class, and chances are really good at this point that it's going to be RiskFive. As far as the hiring climate, definitely there's huge need to hire people in hardware today, and I think people are trying to figure out how to accelerate the advancement of people coming out of school. So pair them with just like RiskFive International has created these development partners where we partner with universities and people in industry to help lift RiskFive. Companies are doing that as well. So it's a great opportunity for college students to look into hardware, and definitely lots of exciting things in hardware.
Great. Thanks, Ted. My son is a freshman in college. He is into software, so I will definitely quote you next time I talk to him.
All right.
So, right on.
Yeah. All right. Thank you. Sorry for running late.
No. Thank you, Ted.
All right.
Yeah.